Good evening, ladies and gentlemen. How are you all doing? I'm also well, thank you. So, what do you mean you gave the proper homework? Are you guys ready for tomorrow's semester test? As I see, there's homework specifically crafted for Prof G. Who's Prof G? The spec is simple. Write a program that determines your birthday based on date input, and if the birthday date matches the current date, it should output happy birthday. Date format is entirely up to the professor to decide. On note, the program must be programmed in BrainFunk. That's cool. So you actually gave him an assignment. And is he keen to doing it? That is well done on him. Seems like it's a very interesting lecturer. So are you guys ready for tomorrow night's semester test? So half of this class I'm going to dedicate to answer questions on the work we've covered for the test if you need help with something. So I'm going to ask you, do you want to have the first half of the lecture being open floor and you can discuss what's happening in your preparations? Or would you first like to do our lecture for this evening in the first half and then continue over to doing questions and answers? Okay, so questions and answers first. So the floor is open if you have any questions. Would you like me to go through everything? As soon as there's no more discussion amongst everyone for questions, then we can continue with the lecture. Or I find it usually it works when we have an open session. So some of the other students may explain something in a different way. So the floor is open. Yes, Mr. Levuyo.
So yesterday, sir. Good morning. Good evening, sir.
How are you?
Hey, I'm actually excited, if I'm being honest.
That's good.
Yes, sir. So I have a question, sir, about yesterday's answer when it came to about Galileo, sir. I came to
Yes.
argue about that answer, sir. That it said that shows what was it? That Galileo's observations showed that uh the
Let me
moon's.
just, I'm just opening it up on my side again. Just trying to find it. Okay. I'm just opening it up. Okay, come on. Okay, I'm going to share my screen as well if that will work. Can you remember what was the question number?
No, sir, but I think it was in the double digits.
Okay, let me quickly see if I can find it. Question 17, got it, thank you. So let me quickly just share my screen. Okay, so you guys should be able to see my screen now. Let me perhaps just zoom in a little bit. Is this a little bit better?
Yes, sir.
Or should I zoom in a little bit more?
A little bit more would be better.
Okay, so let me zoom in a little bit more. And this should be big enough now.
Yes, sir.
Awesome. So let's hear what your argument is.
So that answer, so C is right as well, sir. But then, if I remember correctly, sir, Galileo and Kepler were alive during the same period of time. So then,
Yes.
sir, Kepler found out that, well, Kepler discovered his laws, so but then like he didn't necessarily have observations to back it up that
Mm-hmm.
we lived in a heliocentric universe. So
Yes.
so wouldn't Galileo's observation sort of prove Kepler's laws right? And so wouldn't that also sort of prove that Jupiter orbits the sun, but like as well as the Earth can move, like the Earth can move without leaving its moon, as well as that
Yeah,
answer.
that is also true. So what you are arguing is that we perhaps add another option that says B and C,
Yes, sir.
or only B.
B and C.
Okay, so I agree with you on that, and well done on picking it up. And that's why we are science students. So scientists are supposed to be open for interpretation and a bit of debating on questions. So the rest of the class, what do you think about this argument? So, Mr. Gutsia, why do you think it's just B? Yes, Mr. Gutsia.
Good day, sir. I agree with Lavoya, but I actually think it's just B. I think that the Earth moves without leaving its moon behind is kind of, for me, it's just a bit too obvious. I think we'd be able to observe that regardless of whether or not we observe the moons of Jupiter, which is why I think it's actually just B.
Okay, that also makes sense. What does the rest of the class think?
So I want to disagree with that.
Okay.
So
So you would
because
say B and C.
yes, sir. Because in the with the other model of the Earth, I forgot who it was when he's when that person said we move around. Well, the whole the universe moves around the Earth, right? I wouldn't say it's obvious that the Earth moves around. I mean, the moon moves around the Earth because there's some days where you can't necessarily see the moon, and so it's actually hard to say that the moon is always moving around the Earth, if that makes sense.
That makes completely sense. And I agree with you on that as well. So, any other thoughts of any other person? So if there's no objection, let's do this for now. So I think that B implies C, as if Jupiter orbits the Sun, one can deduce the Earth moves like Jupiter. Yes, we can say that as well. So I think let's say B and C. Is everybody in full agreement with that? Awesome. Thank you, Mr. Lavuyo. I really appreciate you putting effort into this question and debating it a little bit. And that is what I like about open sessions, so very well done. So a few other questions. Let's just do this. Yes, so today I just got a little bit busy with my own research. So tonight after this lecture, I will finish the formula sheet, and that will be part of the instruction set of the test, so you will always be able to see the formulas. Okay, so let me go scroll back a few of the comments and just go through the questions you asked, and just quickly get my copy of the textbook. So, good evening, sir. Can you please explain the example brief from Reasoning with Numbers if the star size section in chapter 8 of Family of Stars? Okay, so easiest way will probably be if I will share my screen with the textbook. Okay, it's opening up on my side. Okay, yes, let's go to chapter 8. Okay, I'm going to share my screen. Okay, so you all should be seeing my screen now. So let me just go back to the question. Explain the example B from Reasoning with Numbers. So can you remember which page it is on the textbook? Reasoning with Numbers, this one. The star size section. So real notes, paradox distances, a star size. That one, A3. Okay, let me go to A3. Okay, is the size big enough, or would you guys like me to zoom in a little bit? Okay, so let's go through Reasoning with Numbers. Let's go through this one. So the luminosity L of a star depends on two things, its size and its temperature. If the star has a large surface area from which to radiate, it can have a high luminosity. So recall from the discussion of blackbody radiation in reasoning of number 6.1 that amount of energy emitted per second from each square meter of the star's surface is omega t. Just the star's luminosity can be written in surface area in square meters times the amount of radius from each square meter. So this is just a formula that you can use for the surface area. So remember, for the formula sheet I'm going to give you for tomorrow, okay, if there's load shedding, I will upload the recording of this immediately afterwards. You're more than welcome to contact me anytime before the test tomorrow. So we will have our normal just formula. So because a star is a sphere, you can use the formula. So the surface area is 4 pi r squared. So we submit 4 pi r squared just into this bracket space where the surface area is. So this may seem complicated, but if you express luminosity, radius, and temperature in the proportion to the sun, you get a simpler form. So remember L with the circle and the dots, that stands for solar. So solar luminosity, a normal luminosity, solar radius, normal radius, and then the temperature. So if you express it in this way, then we have a nice ratio formula we can work with. So example A, suppose a star has 10 times the sun's radius, but only half the temperature. How luminous is it? So now 10 times the radius, so the radius of our own sun will be 1. So half the temperature, we plug it in. So this will see the star is 6.25 times the sun's luminosity. Now we go to example B. Suppose you measure the apparent brightness and parallax of a star and thereby determine its intrinsic brightness. The star's spectrums show that its surface is 2 times hotter than the sun's. This allows you to correct the intrinsic brightness to include non-visible radiation, so you can calculate that its total luminosity is 40 times the luminosity of that of the sun. So what is the radius of the star relative to the radius? So now we just need to solve for the radius. So yes, the sun's radius is always used as the solar radius. And solar mass is always the sun's mass. So from there, we just plug in our values and we solve for the radiuses. So the radius is 1.6 times. So this is just the relation. So this means that a star is 60% larger in radius than the sun. Awesome. So let me see if I missed anything else. Let me go through. Okay, can we look at blue shifting versus red shifting? It's the next one. No problem. So I'm glad I could help. So blue shifting versus red shifting. So the easiest, let me see if I can quickly find a nice illustration. So let me see if I can find a few things that might be able to help with this. Okay, so I found an image for explanation. So what's meant with red shifting and blue shifting? Red shifting and blue shifting is not literally the frequency or wavelength changing. So if we look at a spectrum, so this is a absorption spectrum of an object. So this is the plain normal absorption spectrum. But if something is red shifted, it's moving away from us. Blue shifted, it's moving. So red shifted away from us, blue shifted towards us. So when it is red shifted, you'll see these lines are a bit moved to the right hand side. And then blue shifted, it's moved a little bit to the left hand side. So that's where the terminologies come from, red shift and blue shift. But what is actually happening, as we have done with the Doppler effect, so if I get a whiteboard, if we have our car, and our car is driving this way, and we have sound waves, it means these sound waves, this side, will be compressed, and the sound waves this side will be stretched. And that will give you, when a car drives past you, that sound effect. The same thing happens, so this is sound waves. So sound waves, the physical wave, here is compressed and here it's stretched. But the same thing happens in electromagnetic radiation as well. But in electromagnetic radiation, we cannot compress the waves. So what's happening, it seems like it shifted a bit to one side and the other side. So if everything is moving away from us, then it's red shifted. And if it's moving towards us, it's blue shifted. And that's why we can determine that everything in the galaxy is red shifted. So it's not physically red or physically blue. If we go back to this image, I'll be with you now, Mr. Lavuyo. So if we go back to this image, this is what we get. Mr. Lavuyo, you can go ahead.
So does that mean that even so for example with the Doppler effect, and your example with the siren, so say you only play one type of note, musical note.
Yes.
Does that, so you saying that note doesn't change?
So it all depends on the observer itself. So for example, we are in an ambulance driving and we have the siren going off all the time. We sitting in the ambulance will hear the same notes of the siren over and over and over again, because with us, the siren and sound waves are moving with us. An observer, if we are observing someone standing on the outside, for them the pitch will change, but the pitch changes because this is propagating through a medium. Sound needs to propagate through a medium such as water, such as air, such as solid material. But electromagnetic waves can travel through a vacuum. So that's why we don't have a pitch change, as you can see in electromagnetic waves.
Yes. So and so also with that idea of what's that thing called, when it comes to collecting light from distant objects, you say it becomes harder to observe because the light rays are much more spread out, right?
Yes.
And so does that phenomena also happen with sound?
Yes, that does. So what everything comes down to, if we look at any, let's just get a whiteboard out. So, for example, everything comes down to flux density. Thank you, Mr. Groenewald, for the definitions. That helps. So basically what happens is what you're talking about, Mr. Levio, if we have a, let me try and draw this to the best of my ability. So we have a plane, and we have incoming, could be light rays, can be sound waves, can be electromagnetic rays. If we are clever, if our source, for example, is over here, then a lot of its particles can pass through this detector, our surface area, meaning our flux density is very high. But if we have the same size detector and our source is far, 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 far away, so let's draw it over here and smaller because it's far, then we have going this way, 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 perhaps going this way. So we can see from all of these source points from it is crossing our detector, so we will have a large flux density, meaning the closer the objects is, the better we can pick it up. And now we have the same detector. These two objects are emitting the exact same power, but this one is only further away, and we can see a lot less of its particles is hitting our detector because it spreads out further the further away we are. The same principle is with sound as well. If you are, for example, at a big rock show in the FNB Stadium, you are standing in front of the stage, the music will be ear deafening. If you stand at the back of the stadium, you will see the sound is a bit manageable and you can talk to your friend. If you're outside the stadium, then it's much better. If you are a kilometer away of the stadium, then you can barely hear the music, and that's how it works.
Thank you, sir.
Pleasure. So going through the other comments, so how do we obtain the unshifted spectrum? So that is something quite easy we do. So we all know, let me just quickly get this. So we all know the formula for frequency. We know F equals 1 over the period, right? And we also know F equals C over lambda. Awesome. But we can also write this as, come on, what is it? V equals F lambda. And that's just basically these two equations where we say V equals to C, right? So that means we can write our frequency. So let's get the other form. So that means we can write, use this equation, F equals, not C, sorry, V over lambda, meaning we can work in this form. So if we rewrite this as V equals F lambda, it all depends on what you prefer. Some astronomers like working not in frequency of electromagnetic wave, but the speed of the electromagnetic wave. So if we have something like this, let me get that image back. instead of saying when this unshifted signal we have, instead of using frequency, we say this component has this speed, this component has that speed. So what we do to calculate these shifts in the end, let me get a whiteboard again. It's a stupid functionality now that I lost the whiteboard. But what happens is, if we have, again, our F equals V equals F lambda, and that is basically C equals F lambda, but we can now calculate what the rest speed is corresponding to that frequency, and we know what an unshifted signal looks like. It's a pleasure. So I'm just working through all the comments, making sure I don't miss anything. So a question from Mr. van der Berg. Sir, how does a black hole get its accretion disk? Because I was thinking, and the supernova would blast away the other star if it was in a binary system. Okay, so how does it get its accretion disk? We will discuss that in the chapter we are finishing this evening and in our new lecture material as well. But basically what's happening is, inside most galaxies is a supermassive black hole. And then the rest of our stars in the galaxy orbit around it. And we will have our different spiral arms, traveling around in a circle. But the supermassive black hole in the galaxy is not one star that went supernova and formed a black hole. It must have been formed by pulling in matter during centuries and centuries and centuries. So what a accretion disk does is, everything, say for example our own sun, the Earth and our planets are on stable orbits around the sun. But in a black hole, most of our stars are in stable orbits around a black hole. But in the center of the galaxy, the area closer to the black hole, because the gravitational pull is stronger, contains much more stars than the rest of the galaxy, and also a few other materials. So inside the closer or the inner core of the galaxy, or the nucleus, some interesting stuff can happen. And then from there, material can move due to eccentric orbits and get started pulling into the black hole, and therefore it starts getting an accretion disk. Yes, Mr. Lebuya.
So am I correct by saying that the size of a black hole is like it's infinitely small, like inside the black hole it's infinitely small?
Yes, you can, because if you look at the Chandrasekhar limit, the radius of the black hole basically is zero. So it's basically a singularity, a point. But so far we have no idea what's happening inside a black hole. The only thing we can observe is the accretion disk around a black hole. So that could be right.
But then, so how do we measure the size of a black hole? Do we measure, when we say the size of a black hole, are we measuring where the event horizon is?
So it's like the talk I showed you last week, but how we measure the physical size of the black hole is, let me do it. If this is the black hole, and I'm drawing it now sideways, then everything, the light, or not light, the electromagnetic range of the an accretion disk is bended around the black hole. So when we would put a theoretical, let's say, screen this side, then these electromagnetic rays, color, will hit the screen. So where these light, the electromagnetic rays pass, comes to us, this is also on the edge of the event horizon, and then we are left with an image basically of the shadow of the black hole. So this part over here, and that we can measure.
And so that's how we determine the size of the black hole.
Yes.
And so do the do different black holes have different characteristics based on their size?
The characteristics will remain the same. The only thing that will differ is the force or the power of the black hole.
Okay, thank you, sir.
It's a pleasure. So going through the other questions. So another question about the marks. So as soon as everyone has written the test, so at 8 o'clock, just after, because I just have to make sure there's no technical difficulties. But as soon as everybody has done their test, then the marks will be available. So another question, can you explain the apparent visual magnitude of a star and what it tells us? So apparent visual magnitude, so that brings us back to one of the earlier lectures. Okay, so just going through the textbook, so it was in one of the early chapters we did apparent visual magnitude. So what happens if there's load shedding during the test? So just please contact me if there's load shedding and you can't log back in. So that means you will have to complete your test after your load shedding. Awesome. Can you guys, okay, so yeah, the apparent visual magnitude. So I'm going to just share my screen. So for your question, the apparent visual magnitude describes us how bright an object is. So we can see here the limit with our human naked eye is magnitude 6. The Hubble Space Telescope can see to around about magnitude 27. The sun is sitting at minus 27. Full moon is roughly at about minus 12, minus 16. So if we go through this example, we can convert between the magnitude and flux's brightness of the magnitude scale. So one thing that we astronomers have decided is, if we can see over here, two stars that differ by 1 magnitude must have a flux ratio that equals the fifth root of 100. And that is a definition we are working with. So if we then just memorize this equation, so we have the relationship of A, relationship of B, the fifth root of 100, the magnitude, and from there on we can determine the flux or the magnitude of a star, and the apparent magnitude tells us how bright the star is. Yes. So this equation over here, to get it from this form over to that form, is just plain arithmetic. So the definition of flux, let me draw it again. So flux is something you'll use or will learn a lot about, especially if you have a module on electromagnetism. So if we have a surface, let's draw two surfaces. It's one surface this way and one surface this way. And we have particles, or not rather particles, let's for this example call it field lines from an object. So if we have field lines that's perpendicular to the surface, means we'll have maximum flux density. But if our source is parallel to the surface, so meaning there are no field lines is crossing the surface, saying this is our minimum flux. So usually what we try and do with these calculations is we see how much particles, how much field lines, how much energy hits our surface, and that determines the flux density. Okay, so now I have a question. When red shifting or blue shifting occurs, does that mean that light itself is part of the fabric of space-time, as in attached to it? One example I've seen a lot of to represent is where a person would draw a wave on a balloon and blow it up, and this causes the wavelength to become longer. In the illusion, the waves are static. So light doesn't form part of the fabric of space. So light is an electromagnetic wave, and in an electromagnetic wave, something needs to generate it, and it moves through our vacuum of space. So electromagnetic waves are a totally different thing than the fabric of space. If we spoke about the fabric of space, then we talk about what is in space. So time forms part of the fabric of space. And then matter forms part of the fabric of space, but electromagnetic radiation has nothing to do with matter.
So if all of that falls under the fabric of space, what is in between the space? Like what is in between the planets?
So in between the planets, we have, that's what we talk about, the stellar particles or stellar dust. So
But
space.
so isn't space like a vacuum?
Space isn't entirely a vacuum. So there's a common misconception. So space isn't a vacuum. Let me quickly. So let me quickly see if I can. I know it's in. In one of the slides, can't remember. Let me try and find it. Okay, so here I got it. So space isn't really a vacuum. In space, we still find particles. So on average, there are 0.3 atoms per cubic meter in space.
And then, so what's in between those atoms? Since there's so much space in between those atoms, what is in between those atoms?
So in between those atoms, there is, as far as I understand, nothing. But with that in mind, then we can start talking about dark matter.
So basically, there is. So basically, you're saying that there is something. There's always something, but it's nothing that we
Yes,
can observe.
yes. So question, so what does the flux then tell us again? So the flux of a star tells us how much energy is leaving its surface. So what happens is, what I think is so, why is it that light experiences the consequences of expanding universe, just like normal matter does too? Because light forms part of the electromagnetic spectrum. The electromagnetic spectrum also has the consequences. So what's happening is in electromagnetic waves, if there's something with an immense amount of mass, then it can bend electromagnetic waves. And Einstein has predicted that in his work, and I've done mathematical models on that as well. Yes, you can say it's because of the particle wave duality, but it's usually to do with the mass of an object, so there's an effect between that as well. So I'm not a particle physicist, but if you're interested in that kind of work, you will do it a lot in your third year. So no question, Mr. Lavuyo, I said you have a question about the assignment?
Yes, sir. So when you're measuring the moon, so there is a point where you can't necessarily measure the height above, like above the horizon, because like eventually, the moon ends up being 90 degrees above, like being 90 degrees from the horizon, and I don't think you can measure the distance from that. So is it okay if you, like, if on all days you don't necessarily have a measurement above the height above the horizon?
Yes, you can even use software like Stellarium to help it. But let me show you in essence what I'm after, and hopefully you've started noticing it. So this is called almana. So when you observe the moon from the exact same place every day at the exact same time, you will see the moon creates this 8 or infinity figure. So with a minimum of 10 observations, you will only see a part of it depending on where you start observing it. No, you should not panic because you only did 10 observations. So 10 observations means you only see a small part of it. So I was hoping through the observations that you guys will, in your research you are doing, put everything together. And the same thing happens with the sun as well. Let me see if I can quickly get an image of it. I'll be able to, so let's get this one. This should work. Let's get a different one. Okay, you're going to upload these images.
So, and as a scientist, so how do you know when the data you're taking whether you're being biased. So like for example, the other day, so we were one of these practicals that we were doing. So we had to measure um gravity. What is the acceleration of gravity? So I was wondering, like during an experiment, you will make mistakes. And
Yes.
I was wondering, when do you know that what you did, like whether you should record the data that you did or whether you're being biased about the data that you're taking in?
So usually what you look at, see if you're biased, is you need to determine in your measurements what is the size of the error you can make. So what is your smallest error you can make? And then you just use statistics and plot in that error. So for example, if you measure something with a 30-centimeter ruler, meaning the smallest measurement on a ruler is a millimeter, meaning the smallest error you can make is a millimeter. So it depends on your error fraction. So if you're doing your experiments and you start realizing your error is way too big, then you can start worrying about results. And the other thing is you need someone to come to the same conclusion. So for example, for myself and other scientists working, if you discover something new or have an experiment, then practice dictates you need at least 2 or 3 other research groups or other institutes to duplicate your experiment and see if they have the same results. So therefore, you can eliminate any biases, eliminate any statistical anomalies, and also make sure that no one screwed up something accidentally.
So it is possible that you can make mistakes when it comes to your experiment and you can just get a result that's not there.
Yes, that can happen. That has happened to me quite a few times.
Thank you, sir.
It's a pleasure. So this is also a sun almanac. So each day of the year, if you take a picture of the sun, you will see it also creates this figure. It all depends on where you are on your longitude and latitude around Earth. But it can also look like this. Again, all depending on your longitude and latitude, if you're northern hemisphere, southern hemisphere, how far north you are and how far south you are. So I was hoping with your minimum of 10 observations that you were able to find something like this. And this image is unique to Earth because we orbit Earth at a specific distance. So the figure we are creating around this is the figure we make while traveling around the sun. So on different planets, it will look a lot different.
So would the Earth look the same from the perspective of the moon?
Yes. No. It won't because no, it won't. It will look exactly the same from the moon. Because remember now, the Earth is a big body and the moon is a big body. And while we are going around, if you're on the moon going around Earth, the moon is not inclined at such a steep angle that we will see it in this figure. So only places we can see this is observing the moon from Earth and observing the sun from Earth.
So this is basically due to how the axis is what is it called? How the axis has deviated from its true north.
Yes, exactly. And the path we follow around the sun.
Okay, thank you, sir.
Pleasure. So do you guys have any other questions for tomorrow's test? Okay, so can we talk about star names? So what would you like to know about star names? Okay, so that was actually one of the questions I asked in the mock test. So let me just share the mock test, share application screen. So this is actually quite interesting. It's in a textbook as well. Neil deGrasse Tyson has a 40-minute lecture, or not for a 40-minute lecture on star names themselves. But most star names are Arabic. So if you go and look at star names during the century, about 70% of all star names is Arabic. And if you ask why, if you go back to when most of the stars were named, you look for the year from year 10,000 to year 14,000, year 1,000 to year 1,400, then you will see there's a lot of scientific development in the Middle East. And have you ever thought about algebraic equations, algebraic Arabic? So a lot of the math we use originated in the Middle East between the year 1000 and the year 1400. So that's why when you look at a few of symbols, especially in algebra Arabic, it is from the Arabic system they used. But somewhere in the Middle Ages, in the Middle East, prophets popped up. And then they started dictating that science is bad, math is bad. And then the Middle East stopped the scientific and mathematical development and haven't contributed anything towards it ever since. And that's why the Middle East is in such a mess today. So when I took photos of the moon, it formed an arc that resembled a parabolic arc. Is that a problem with my measurements since it does not look like the pattern? No, it's not a problem because when you took the photos, you will only see a portion of it. So if it's a parabolic arc, depends on where we are on the 28-day cycle of the moon. So that is why what's happened in the Middle East. So basically due to religion, all scientific breakthroughs has basically gone to zero. So Neil deGrasse Tyson also has an interesting talk about it. So if we look at Nobel Prize laureates, people who won Nobel Prizes, if you go let's take this back a notch. If we look at sports teams, if you just purely look at statistics, a country with a larger population will have better sports teams because there are more people. You can pick the best of the best of to represent you in a sports team. So that's why a country with a large population will always do better in sports than a country with a smaller population. Because you have a larger pool, you can pick people that's the best of the best of the best. But, so the same principle will count towards Nobel Prizes as well. So the country with the biggest population will probably have the biggest Nobel Prize winners, and a country with the smallest population will have the least Nobel Prize winners. But if you look to the Middle East, if you put all the countries in the Middle East together, you have an extremely large population of Earth in the Middle East. But how many people in the Middle East you guys think have won the Nobel Prize? Seven, a total of seven. Yes, Mr. Levio.
So, out of curiosity, sir,
Yes.
what kind of physics do you use, as an astronomer, sir?
So physics, the physics I used most of the time is electromagnetism.
Only, sir.
Yeah, so that's the field I use the most, is electromagnetism and electricity. But that's due to the research I'm doing. So it all depends on what research astronomers is doing. So I look at electromagnetism because I look at new and better ways we can detect signals from space. So to detect better signals from space, you need to understand electromagnetism better, and that's the physics I use most of the time.
And then, so because so some astronomers, I mean not some, because most astronomers depend on data. So and like you get some missions where they might take years to actually even establish. So doesn't that sort of hinder like the development of astronomers, like with in terms of furthering their career, because they don't necessarily have enough data to work with. It's mostly about old type of data.
So yes, we are still getting new data from telescopes. We are working every day. We just need to write a proposal and you can get data from telescopes. But because astronomy is such an old science, we have data going back many and many of years. And because our computer science techniques and computer scientists has caught up, we have now better ways to analyze previously old data and find things that we have completely missed.
So what about the astronomers that depend on data for example, like the Cassini mission? So um aren't there scientists, astronomers that depend on specifically that kind of data, like where they um structure their careers around that one specific mission?
Yes, so they are involved from the beginning of that mission, from the creation of the device, planning what data will be needed until the launch of that spacecraft. And while the spacecraft is uh, traveling to where it needs to be, those scientists will work on other projects until that spacecraft reach there and they will get the data. And so you actually don't work on one project, you work on multiple projects at the same time.
Okay, thank you, sir. Makes sense.
Pleasure. So coming back to the point I want to make, so if you look at United States, that has a lower population density than the Middle East, the United States has 390 Nobel Prize winners. And that's due because some people in the Middle Ages or Dark Ages decided that math science is evil and the Middle East went to a standstill. So Ooh, I have actually no idea who might win the Nobel Prize this year. But if I would put a bet on it, I would probably say it would be someone from the Event Horizon Telescope, or it would be a particle physicist. One of those categories. So, do you have any more questions on the test tomorrow, or can we start with tonight's lecture? Oh yes, that's the one I missed. Black body radiation. So, Mr. Visagie, what about black body radiation? Okay, so let me quickly see if I can find black body radiation. Can you remember which chapter that was in? Chapter 6 or chapter 7? Let me quickly see if I can go for a textbook. Okay, chapter 6 is spectra. So quickly see if I can find it. So yes, I have it. So it's in chapter 5 is on light and telescopes. Page 106. Thank you. So I'm going to it now. Okay, I'm going to share my screen. So it's this one. Okay, so Ms. Visagie, you are comfortable with what black body radiation is? Okay, so what black body radiation means is everything around us radiates energy. And that energy of black body radiation is represented in a form of heat. So if you think about it, if we put an ice cube through an infrared imager, it will still radiate energy. Although it's very cold, it still has energy and still has heat. The colder we go, the less black body radiation we have. So everything in the known universe emits black body radiation. Even though it's extremely cold, it still emits black body radiation. So for this example, black body radiation is described by two simple laws that can be expressed in precise mathematical form. So many objects give off radiation as black bodies that these two laws are important principles in analysis of light from the universe. Wien's law expresses quantitatively the relation between temperature and wavelength at which black body radiation radiates the most energy. Its wavelength of maximum intensity, written in a form of conventional units, is, you can write as this. So wavelength, so for visible light will be in nanometers, is 2 times 9 times 10 to the power 6 over the temperature in Kelvin. So that is the wavelength in nanometers of maximum radiation intensity emitted by black body equals 2.9 million divided by the black body's temperature on a Kelvin scale. This law is a powerful aid in astronomy. For example, a cool star with a temperature of 2,900 Kelvin will emit most intensely at a wavelength of 100 nanometers. So all you need to do is you need to remember this formula, meaning if you have the temperature of the star, you plug in the temperature of the star in Kelvin, and you will know what frequency we will pick up most intensely from that star, and you put that on the EM scale, and we will know what frequency that is. So now 1,000 nanometers, which is the near infrared part of the spectrum. In contrast, a very hot star with a temperature of 29,000 Kelvin will mostly intensify wavelengths at 100 nanometers, which is ultraviolet. So this is Wien's law. So does that mean no object can have a temperature of 0? So objects can have temperatures of absolute 0, but so far we can only create absolute 0 temperatures in lab conditions. Oh yes, and from the frequency we can find which part of the spectrum the radiation sits on. Yes. Can I do an example calculation? So yes, wavelength, we can convert wavelength to frequency. So here we're working with wavelengths. So 100 nanometers is ultraviolet, but 100 nanometers you can convert to frequency again. Because we know F equals C times lambda. What do you want me to do an example calculation on? Okay, this formula. So let me get a whiteboard. So let's do these calculations straightforward, but let's do this calculation. So we have lambda max equals 2.90 times 10 to the power 6 over temperature in Kelvin. So now I tell you we have a star of temperature 2,900 Kelvin. At what wavelength will the maximum intensity be? So we say lambda max equals 2.90 times 10 to the power 6 over 2,900. And that will give you 1 times 10 to the power. So plug it into your calculators. Or rather be 9 meters or nanometers. So yes, in science, so usually they will specify if the SI unit will be in Fahrenheit or Celsius, but usually the SI unit is in Kelvin. And then this wavelength, we can now change that to frequency. because we know frequency equals c times lambda. We know what the wavelength is, we plug it in, and then we know what our frequency is. And then I saw another question on the HR diagram. So let me find that in the textbook quickly. Got it. So here in the HR diagram, the HR diagram describes the life cycle of stars. So once a star is born, it will fall somewhere on this main sequence line. Sorry about it, guys. It seems like load shedding has just started in my area. Can everyone hear me? For some reason, my area is not scheduled to have load shedding this evening, but for some reason the power went out. So sorry about that. So I'm going to share my screen again. So the HR diagram describes the temperature versus luminosity of stars. So here we can see the temperature is going hotter this side and luminosity is going higher when we go up. So on the left corner means if we have a high supergiant, so a blue supergiant, it means it is very high temperature and mean it is very luminous. So here we will see more luminous stars, more cooler stars, and fainter stars in the HR diagram. So the HR diagram basically describes the luminosity and temperature of the star, and from the luminosity and temperature, we can determine its size and other characteristics. Because a B star is hotter than an A star. So I will post the formula sheet later this evening. I still need to complete it. So how much math for stars? Probably going to be 4 questions for math. Yes,
So I have an unrelated question. I'm just curious. So scientists complain about not having funding for research. So with all the geniuses that are working on physics, so why aren't some scientists allocated to find ways to generate money? For example, so you have trust funds, the trust fund, investment bankers. So they usually invest their money in the stock market. So why don't scientists do the same?
That is actually a very complicated question, and that basically forms down to politics. So what people really don't realize is, if you take NASA, for example, for every dollar invested in NASA, it generates $7 in return. But politicians, that's the other way around, because to do research, the government puts checks and balances on everything. So to take research money and go to the stock market is a big no-no, because then they argue you can lose the money, you can make money, you can steal money. So we work on research grants, and yes, it comes to conflict of interest. So we work on research grants, but unfortunately, these research grants depends on who is the politicians and what a politicians wants to do with their careers. So if you have a politician that wants to help science, then yes, science gets a lot of funding. If you have politicians that doesn't care anything about science, and all that they care about is how fancy their lifestyle can be and how they can help the economy, then science goes down the drain and you don't get any funding.
But then, I mean, so can you not privatize science? Because it seems like where scientists are more dependent on the government than government is dependent on scientists.
Yes, so in recent days, some organizations have started doing public-private partnerships. So just to put it in perspective how messed up this really is, I know university fees are extremely high, but if you think about it, most of the universities in South Africa are public universities. And public universities are supposed to be subsidized by the government to be able to do research and to have funding for operational costs. So how it's supposed to work is the university is supposed to get 75% funding from the government, and the other 25% the university is supposed to find somewhere else. Currently, universities in South Africa are 30% subsidized by the government and need to find funding elsewhere. So to get funding, so that's why, unfortunately, the free education in South Africa will currently not work, because where will the universities get their funding from? We need the class money for one, operational costs, and then secondly, to keep everything maintained and to do research. So there's a lot of alumni that we try to approach to donate to the university, set up deals with the private sector to get funding, but this is the situation we are currently in.
Thank you, sir.
Pleasure. So do you guys have any more questions? So if you guys have any more questions, I would like to go on and finish our lecture slides of last night. I'm a big Elon Musk fan. His organizations and companies is doing great. So that's why he can do the work he does, especially with SpaceX, because he has the funding for it. And that's why the space race now to go to Mars is led by private companies such as SpaceX, Blue Origin of Jeff Bezos, Boeing, Virgin Galactic, because private institutes now has funding to do it, and government institutes does not have funding to do it. So the problem is, if you want to go to the number one organization that's supposed to do these, are NASA, but NASA currently has 1% of the entire US federal budget at its disposal. Back in the Apollo days, NASA had 30% of the entire US funding available to it, and now it only has 1% available. And if something goes wrong, for example, if there's a launch, so back in the day, a space shuttle launch usually cost about $1.4 billion a launch. If something goes wrong, then you need to explain to the Senate what went wrong, and you need funding for another space shuttle mission. But in private sector, if something blows up, we have an accident, it's just, oops, we have money, we'll do it again. Yes, Lockheed Martin as well. I'm a big fan of Lockheed Martin. So I have ended off last night with this slide. So now we're going to start looking at stellar populations. In the 1940s, astronomers realized that there are two families of stars in a galaxy. They form and evolve in similar ways, but they differ especially in their abundances of metals. Population 1 stars are metal-rich, containing 1 to 3% metals, whereas population 2 stars are metal-poor, typically containing less than 0.1% metals. So the difference is clearly evident in spectra. So In the upper line over here, we can see many metal lines, and here we can see weak metal lines. So again, here in image A, we can see the difference between spectra of population 1 stars and population 2 stars is dramatic. Then image B, a graph of such spectra reveals overlapping absorption lines of metal completely blanketing the population of population 1 spectrum. The lower spectrum is that of extremely metal poor star with only a few weak metal lines of iron and nickel. So this population 2 star contains about 10 times less metal than the Sun. HR diagrams of star clusters reveal that population 1 stars are relatively young and population 2 stars are old. Population 1 stars belong to the disk component of the galaxy and are sometimes called disk population stars. They have nearly circular orbits in the plane of the galaxy and formed within the past few billion years. The Sun is a population 1 star, as are the type 1 Shepard variables discussed in this chapter. Population 2 stars belong to the spherical component of the galaxy and are sometimes called the halo population stars. These stars have randomly tipped orbits ranging from circular to highly elliptical. They are old stars that formed when the galaxy was young. The metal-poor globular clusters are part of the halo population, as are the RR, Lyra, and type 2 Shepards. Further observations show there is a gradation between populations. Extreme population 1 stars are found only in the spiral arms. Slightly less metal-rich population 1 stars, called intermediate population 1 stars, are located throughout the disk. The Sun is an intermediate population 1 star. Stars that are even less metal-rich, such as stars in the central bulge, belong to the intermediate population 2. The most metal-poor stars are those in the halo, including those in globular clusters. Those are referred to as extreme population 2 stars. The two populations of stars in our galaxy are clearly different. These two differences are clues to the history of the galaxy. So here we can see the difference of population 1 and population 2 stars. When you observe population 2 stars, such as those in the halo, you are looking at the survivors of the early generations of stars in the galaxy. The first stars formed from gas that was metal poor, and the only survivors of these early generations are low-mass, long-lived stars. Their spectra, which indicate the composition of their atmospheres and not their cores, still show the composition of the metal-poor gas from which they formed. Population 1 stars, such as the Sun, formed more recently, after the interstellar medium had been enriched in metals, and the spectra shows stronger metal lines. Stars forming now have even higher metal abundances. So you are the same age as the universe, because matter can never be created or destroyed. Because astronomers know how to find the age of star clusters, they can estimate the age of the oldest stars in the galaxy, given a lower limit to the age of the entire galaxy. The process is straightforward, but uncertainties make the easy answer hard to interpret. Does that mean the amount of matter in the universe has not changed? No, it has not. Because matter cannot be created nor destroyed, it can only change form. Yes, that is interesting. So the oldest open clusters are 9 to 10 billion years old. These ages come from the turn-off points in the HR diagrams, but finding the age of an old cluster is difficult because old clusters change so slowly. Also, the exact location of the turn-off point depends on chemical compositions, which differs slightly among clusters. Finally, open clusters are not strongly bound by gravity, so older open clusters may have dissipated as their stars wandered away. It is reasonable to suppose that a galactic disk is somewhat older than the oldest remaining open clusters, We suggest that the disk is at least 10 billion years old. Yes, that is the theory we are going with, that matter still exists inside the black hole in some way. Globular clusters have faint turn-off points in their HR diagrams and are clearly old, but finding these ages is difficult. Again, slight differences in chemical composition make noticeable differences when calculating the stellar models from which ages are determined. Also, to find the age of a cluster, astronomers must know its distance. Parallaxes from the Hipparcos satellite may allow astronomers to improve the calibration of the Sherpades and RR variable stars. And careful studies with the newest large telescopes has refined the chemical composition and better defined the HR diagrams of globular clusters. The best analysis of all of the data suggests that the average globular clusters are about 11 billion years old. Although some globular clusters are younger than that, and some are older. Studies of the oldest globular clusters suggest that the halo of our galaxy is at least 13 billion years old. Observations of stellar populations and clusters show that a disk is younger than the halo. So you can combine these ages with the process of nucleosynthesis to tell the story of our galaxy. The lack of metals in the spherical component of the galaxy tells you it is very old, a fossil left behind by the galaxy when it was young and drastically different from its present disk shape. The study of element building and stellar populations leads to the fundamental question: how did our galaxy form? In the 1950s, astronomers began to develop hypotheses, sometimes called the monolithic collapse hypothesis, also known as the top-down hypothesis, to explain the formation of a galaxy. Later observations forced the realization of that hypothesis. So the top-down hypothesis is: the spherical cloud of turbulent gas gives birth to the first stars and star clusters. The rotating cloud of gas begins to contract towards its equatorial plane. Stars and clusters are left behind in the halo as the gas cloud flattens. New generations of stars have flatter distributions. The disk of the galaxy is now very thin. This is the monolithic collapse. The monolithic collapse hypothesis says that a galaxy formed from a single large cloud of turbulent gas over 13 billion years ago. That cloud contracted from our galaxy. As gravity pulled the gas inward, the cloud began to fragment into smaller clouds, and because the gas was turbulent, the smaller clouds had random velocities. That caused the stars and star clusters that formed from these fragments to have orbits with a wide range of shapes. A few were circular, most were eccentric, and some were extremely eccentric. The orbits were also inclined at different angles, resulting in a spherical cloud of stars. The spherical component of the galaxy, of course, these first stars were metal poor because no stars had existed earlier to enrich the gas with metals. The second stage in this hypothesis accounts for the formation of the disk component. As the gas clouds in the originally spherical cloud collided, turbulent motions in the gas cancelled out, as do eddies in recently stirred coffee, and the cloud was left with a uniform rotation. A rotation, low-density cloud of gas cannot remain spherical. A star is spherical because its high internal pressure balances its gravity. But in a low-density cloud, the internal pressure is much too low to support the weight. Like a blob of pizza, though spun in the air, the cloud must flatten into a disk, eventually producing the galaxy's disk. The contraction from a sphere into a disk would have taken billions of years, and while that happened, the metal abundance gradually increased as generations of stars were born from a gradually flattening gas cloud. The stars and globular clusters of the halo were left behind by the cloud as it flattened, and subsequent generations of stars formed in flattened distributions. The gas distribution in the galaxy now is so flat that the youngest stars are confined to a disk about only 100 parsecs thick. The stars are metal-rich and have nearly circular orbits. The monolithic collapse hypothesis accounts for many of the Milky Way's properties. Advances in technology, however, have improved astronomical observation, and beginning of the 1980s, contradictions between theory and observations arose. For example, not all globular clusters have the same age, but surprisingly, some of the youngest clusters seem to be in the outer halo. In contrast, monolithic collapse hypothesis says that a halo formed first and predicts that the clusters within it should either have a uniform age, or the more distant ones should be somewhat older. Another problem is that the older stars are observed to be metal poor but not completely metal free. There must have been at least a few massive stars to create these metals during generation before the formation of the older stars now seen in the halo. Can the regional hypothesis be modified to explain these observations? Astronomers suspect that the galaxy began as a large gas cloud containing almost no metals. Models of metal-free stars show that they are very massive. So that first generation of stars evolved rapidly and exploded as supernova, which enriched the gas cloud with traces of metals. None of those massive first-generation stars survive, but the metals they created are detectable in the oldest population 2 stars. It seems likely that a central bulge and halo formed from such gas clouds or from the accumulation of a number of gas clouds. A thick, low-density disk of stars may have formed at an early stage. This would explain the age of the central bulge and the metal in both the older stars in the halo and those scattered above and below the disk. The thin part of the disk could have formed later as more gas fell into the galaxy and settled into the gas clouds of the thin disk where stars are forming today. Perhaps entire galaxies were captured by the growing Milky Way. Astronomers have found streams and rings of scattered stars surrounding our galaxy and hypothesize that they were produced when smaller galaxies were captured, pulled apart and absorbed by our own home galaxy. You will see dramatic evidence in the next chapter that such galaxy mergers do occur. If the Milky Way galaxy, in fact, was partly assembled from smaller units, absorbing several small but partially evolved galaxies, in some of the globular clusters, astronomers see in the halo may be hitchhikers. Astronomers now have evidence that our galaxy formed through merger of a number of smaller pre-galaxy clouds of gas and stars, plus later additions of infalling gas and more small galaxies. So putting this together, we now have a bottom-up galaxy formation process. So mixed clouds of normal and dark matter are drawn together. The first stars are massive, evolve fast, and begin making metals and dust as larger protogalaxy accumulates. More clouds of dark matter plus gas, dust, and stars fall in and begin building a halo and thick disk. Small galaxies are ripped apart by tides and absorbed, adding to the halo and disk. Gas and dust settle into a thin disk where star formation continues. So the bottom-up hypothesis for the formation of the Milky Way galaxy proposes that smaller star systems accumulated to form larger ones. You see how this could have built a galaxy. Start with the top frame, depicting the situation for only a few 100 million years after the beginning of the universe, as small clouds of matter begin accumulating and stars beginning forming in them. In the second frame, the central object has grown larger, and in the third frame, the galactic halo and disk are formed. By today representing the bottom frame, the disk of the galaxy has become very thin. This bottom-up hypothesis for the formation of the galaxy would explain puzzles such as the observed ranges of globular clusters, ages, and metallices. The metal abundances and ages of stars and star clusters in a galaxy seem to be important clues, but metal abundance and age do not tell the whole story. Astronomer Bernard Pagel was thinking of this when he said cats and dogs may have the same age, metallicity, but they are still cats and dogs. So here we can see our planet is in a far edge, the outskirts of the galaxy. So most of the planets found to date lie within about 300 light years from our sun. Yes, Mr. Lavuyo.
So, is there temperature variation within a galaxy?
Within a galaxy?
Yes, so like for example, so the center of the galaxy, is it much hotter compared to the outskirts?
Yes, that is true. So you will have certain areas in the galaxy that there's temperature variation. So usually right here in the center or the nucleus of the galaxy, it will be hotter because there is more interstellar dust and more matter for star formation to occur. So there will be hotter parts near the nucleus of the galaxy.
And so would it be as hot as a star, or less hot?
It depends on what stars is being formed. It all depends on the region of the galaxy you are in. So the temperature of a black hole, we don't know what it is, but we know the excretion disk around the black hole is very hot because it generates X-rays.
So is it mostly the formation of the stars that cause the different temperatures, as well as the secretion disk?
Yes.
Okay, thank you, sir.
Awesome. So do you all recognize this quote, "To boldly go where no one has gone before," and where does it come from? Yes, Star Trek. So this is the end of our lecture. So ladies and gentlemen, good luck with preparations for tomorrow night's test. I will still be available if you need help with questions, as long as tonight it's within reasonable hours, but otherwise I'm still available tomorrow throughout the day if you have questions as well. It's a pleasure, guys. Have a wonderful evening. Try to get a good night's rest, and good luck with preparations. The test, if you are able to do the mock test, the standard of questions are exactly the same. So if you can do the mock test, you will really do good in tomorrow night's test.
So I have a question, sir.
Yes.
So getting into higher graduate degrees, like for example your masters and your honors level. So in physics, so do you really need good marks? Because this degree is really hard, sir.
So it all depends on the program you want to enter. So I just look at prerequisites. So usually to get into a honors degree, you need an average of 65% in your undergraduate degree. And usually going from honors over to a master's, you need a minimum average of 65% for your modules and honors. But when you start a master's degree, you just need a master's degree to do a PhD.
So basically, sir, in most of your modules to get into your honors, most of them need to be above 65.
Yes, your average needs to be 65 or higher.
And so do some modules count more than others, or do you just count all of them as a whole?
You just count all of them as a whole, so what your average is. It all depends. Some honors program doesn't have that minimum prerequisite of 65% average. Some honors degrees only look at your third year modules. You need a minimum of 65% in your third year. So it all depends on what program you want to enter.
Okay, thank you, sir.
Pleasure. No, that's false. If you repeat a year of study, you can still do a master's. No, there's no minimum time to apply. So if you have your bachelor's degree, you can even wait 20 years before you can do an honors. You can still wait another 15 years to do a master's. No, if you fail the module or redid a year, no, you can still get into postgraduate courses.
And so, like, do you have any tips for our students to like sort of get to that level, like to work our way up there?
The tips I have for you guys is if you want to do if you want to go to master's level, PhD level, it is a long and difficult road. So just to give a bit of statistics on, so if you start straight out of high school with a start of a bachelor's, and then you do your honors, you do a master's, you do a PhD, the average person takes about 14 years to go through everything. So you need patience is the one thing. Then the other thing is, remember, failure is not the end of the world. If you fail something, it just means you're not ready at that point in time of your life to do a certain module, to do a certain project, but it prepares you for when you do it again, that you will do to the best of your knowledge and the best of your power. And then from there on, make sure whatever you do is what you like to do. So, for example, if you want to do research, usually master's degrees is research based. If you hate the research you are doing, you are going to hate your master's research. So make sure you enjoy what you are doing, because that is something you are specializing in. That is something you're going to be working with every day. And then lastly, that makes a difference is if you start getting to honors, you will need a supervisor, or other term for it is a study leader that will help you. Make sure you get along with your study leader. So it doesn't help you have a great research project and you have a horrible study leader or supervisor you bump heads with constantly. So make sure you have someone you can actually work with. Yes, that's exactly true. When you have confidence, you have a lot of fun. And when you have fun, you can do amazing things. That is very, very true. So, yes, you can do a PhD directly after master's.
And so to be a scientist, do you need a PhD, or can you just complete your master's and become a scientist?
So to be a scientist depends where you want to be. If you are in academia, so if you're a scientist and you want to work for a university or a research institute, then it is preferred that you have a PhD. You can get away of having a master's, but it's preferred that you have a PhD. If you are a scientist in industry, then you can get away by having a honors degree, but it's preferred that you would have a master's.
And so is there a difference between like the type of work you do in academia versus industry?
Yes, there is. So in academia, you primarily do research and teaching. So the ideal position in academia will be is to have a pure research position. But unfortunately, in academia, there's not many pure research positions. So in academia, usually you have one semester that you have to teach, and the rest of the time you have to do research. And you are evaluated. So we call it KPIs, key performance indicators. So you have to do research alongside the teaching. Where in industry, you can have research positions, but there's also not many pure research positions. Mostly in industry, you will be working on projects. So if you finish one project, you will start a next project. If you finish that project, you will start a next project. And in industry, you will also most likely work with product development. So speaking about computer scientists, if you just have your normal bachelor's degree, so your BSc in computer science, then you're set to work in industry because you have the programming knowledge. So then you can be a programmer, software developer, systems architect. But if you want to do research in computer science, then you would need to have a master's or PhD. So if you're studying computer science and you want to be a software developer, systems architect, systems engineer, then it's fine. Then your bachelor's degree is perfect. But as soon as you start touching on the research aspect of things, want to start doing in-depth research, then you need a master's and PhD.
And so you said 14 years on average.
Yes, so the average person takes 14 years to start with their studies in undergraduate and finish a PhD.
Yo.
There's a lot of people, so there's some rare occasions where people will do it faster, then it will take about 10 years. But the average person takes about 14 years.
And so do you honestly think it's worth it, sir? Like, what is the difference between a PhD and a master's?
So for the best way to describe it, for masters is you are basically mastering a field. But if you go into a PhD is something that has never been done before. So it's completely new. So if you do a PhD, then you become the complete expert on that part of research or field you're entering in.
But then, sir, doesn't that become so doesn't sort of that box you in because like now that's one of so is that topic the only research that you focus on, like that field specifically something that you focus on for the rest of your career, or is it something
No,
that you can
not
change?
necessarily, because once you've done your PhD, you can continue on with research in the topic you've chosen, but you can branch into different sciences as well. So as soon as you have your PhD, you can do research in other fields as well. But it only means to obtain a PhD, you are the ultimate expert in the topic you have chosen.
Okay, thank you, sir.
It's a pleasure. So look here in the chat, computer scientists are underappreciated. We don't even get Nobel Prizes. That is very true. So hopefully a computer scientist will get a Nobel Prize. So we go through. So I always thought the more credits the module, the more it gets weight. So yes, second year modules has a bit higher weighting than first year modules and so on. So is working in a research group as an undergrad helpful? Yes, it is. It's because you are building on your skill set and you are learning skills. So for me, I did my master's at UJO, University of Johannesburg. My PhD supervisor is at Wits University. So if you have no more questions, guys, you're more than welcome to log off. Good luck with the test tomorrow, and I will see you all tomorrow.